Today we've got a nice quick number theory problem that comes from the 1998 Balkan Math Olympiad. And so this is kind of a throwback to a bunch of videos that I did earlier on the channel where I ended up doing lots of problems like this. Okay, so our goal is to find all integers x and y such that y to the fifth is equal to x squared plus 4. And I guess I should point out that no solution is a solution here. So it's possible that there are no such integers. And our main tool here will be something called Fermat's theorem. So let's recall that real quick. It says that if p does not divide a, where p is a prime, then a to the p minus 1 is congruent to 1 mod p. That means when we divide a to the p minus 1 by p, we get a remainder of 1. So just as a couple of examples, so 45 is not divisible by 7. So that means 45 to the 6th power is congruent to 1 mod 7. Next, 17 is not divisible by 23. That means 17 to the 22 is congruent to 1 mod 23. Okay, so let's maybe start looking for our solution here. Well, so the two exponents that we see are this squared exponent and this 5th power exponent. So seeing this squared exponent motivates us to perhaps work modulo 3. So let's see what would happen if we worked mod 3. So if we work mod 3, this will turn into y to the 5th is congruent to x squared plus 1, because 4 is 1 mod 3, and then this is all occurring modulo 3. Okay. Then furthermore, we'd maybe want to look at the case when 3 does not divide x, and then the case when 3 does divide x. So if 3 does not divide x, then that means that x squared is congruent to 1 modulo 3. But that would tell us that y to the 5th is congruent to 2 modulo 3. That's because we'll have 1 plus 1. And there's definitely a solution for this. The solution is y is congruent to 2 mod 3. So that gives us a bunch of possible values for y. But let's maybe lay these out. So some possible values for x would be 1, 2, 4, 5, and then 7, 8, 10, 11, so on and so forth. And the corresponding possible values for y, they're all 2 mod 3. So that would be 2, 5, 8, 11, maybe the next one would be 14, and so on and so forth. But then doing a quick check across those small numbers, you'll see that none of these give us a solution. So none give a solution. So we do get a solution mod 3, but we don't get a solution of the integer equation. And remember, our goal is to have a solution for the integer equation. So that means that since none of these small examples give a solution, and since this is a math contest problem where if there is a solution, it's probably easy to find, and the hard thing is proving that it's the only solution, then we probably want to move on to the next case where if 3 divides x, and see if that gives us anything. So if 3 divides x, then that tells us that y to the 5th is congruent to 1 modulo 3. But that tells us that y is congruent to 1 mod 3. You can check that that's the case. But that gives us a bunch of possibilities as well. So that means that x has to be 3, 6, 9, 12, 15, so on and so forth. It's a multiple of 3. And then y is 1 mod 3. So that means y could be 1, 4, it could be 7, 10, 13, so on and so forth. And then you can furthermore check that none of these small give us a solution either. None of those small values of x or y give us a solution. So putting this all together, that definitely does not prove that there is no solution, but that motivates maybe the guess that there is no solution. But working mod 3 only gives us evidence that there's no solution. So we've got to figure out some other integer to reduce this with. Okay, so let's explore that. So we just worked mod 3 and saw that it seems like there's no integral solution to our equation. So next up, we'd like to reduce mod something else. And let's explore what that might be. We'll notice that 5 plus 1 is not a prime, so reducing mod 6 will not be super helpful. But if we were to square both sides of this equation, we would have y to the 10th power. And 10 plus 1 is 11, which is a prime, which means we can use Fermat's little theorem. So let's maybe work towards that. So let's suppose x and y are integers, and they satisfy this equation here. Y to the 5th is the same thing as x squared plus 4. And now let's square both sides, and we'll get y to the 10 is equal to x squared plus 4 squared. I won't multiply that out. As we'll see, it won't be advantageous to multiply that out. Okay, but now we'll see that 10 is 1 minus 11, like we discussed, so that motivates us to reduce this thing mod 11. But if we reduce this mod 11, we have to work in the case when y is a multiple of 11 or when y is not a multiple of 11. So let's look at the case first when 11 does not divide y. So in other words, y is not a multiple of 11. So that means that we have x squared plus 4 squared is congruent to 1 modulo 11 because y to the 10 is 1 mod 11 by Fermat's little theorem. But then when we're working a prime, there are exactly 2 square roots of the number 1. There's 1 and negative 1. But negative 1 mod 11 is in fact equal to 10. It's 1 less than 11. So that means this splits off into 2 congruences. We have x squared plus 4 is congruent to 1 mod 11, or x squared plus 4 is congruent to 10 mod 11. So again, those are the square roots of 1 mod 11. Okay, so let's maybe continue. So this will give us x squared is congruent to 1 minus 4, which is negative 3, but negative 3 is the same thing as 8 mod 11. And this will give us x squared is congruent to 6 mod 11. And then from here, it's just a matter of making a chart of all of the perfect squares mod 11 and deciding if 8 is a perfect square or if 6 is a perfect square. Okay, so let's do that. So I'm going to do the chart right here. We'll do n, and then we'll do n squared modulo 11 right here. Okay, so we'll consider n equal to 1, 2, 3, 4, 5, 6, 7, 8. I won't worry about 9 or 10 because we'll see that those will already be covered by previous numbers. In fact, 9 is the same thing as negative 2, so when you square it, you get the same thing as 2 squared, and 10 is the same thing as negative 1, so when you square it, you get the same thing as 1 squared. That being said, we'll see the structure build inside of this chart. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, but 16 is 5 mod 11. 5 squared is 25, which is 3 more than 23, so this is 3 mod 11. 6 squared is 36, but that's 3 more than 33, so that's going to be 3 mod 11 as well. 7 squared is 49, that will give us 5. 8 squared is 64, that will give us 9. So as you can see, we have this kind of repetition built into this chart. And now I think it's pretty clear why, in fact, we really only needed to go to this spot right here. And that's because 6 is congruent to negative 5, 7 is congruent to negative 4, and so on and so forth. But the real takeaway here is that the only perfect squares mod 11 are 1, 3, 4, 5, and 9. But that excludes 8 and 6. So let's point out that 8 and 6 are not squares mod 11. So that forms a contradiction, contradicting the fact that x and y satisfy this. And that's because if they satisfy this integer equation, then they satisfy the resulting equation if we reduce mod anything, including 11. Okay, so now let's fit in the case down here where 11 does divide y. So let's see, if 11 does divide y, then that gives us x squared plus 4 squared is congruent to 0 mod 11. Because if 11 divides y, then y is congruent to 0 mod 11. But let's see, moving some things around, we'll see that x squared is congruent to negative 4 mod 11, but negative 4 is 7. So we get this is 7 mod 11. But then looking back at our chart up here, 7 is not one of our perfect squares mod 11. So this does not work either. So either way you put it, this assumed solution cannot be a solution, and thus we don't have a solution. So like I said, I've done lots of other problems like this on the channel. There should be one on the screen right now if you'd like to check it out, and that's a good place to stop.